Okay, so let's continue our discussion related to digital circuit design. And so today we will look at combinational circuit design, something that we've been looking at also for the last one or two lectures. So, but we've not really defined what a combinational circuit is and what other kinds of circuits are. So let's do that first. So digital circuits can be classified into two broad categories. One what are called combinational circuits. And so the idea behind combinational circuits is that the output is a function of only the present values of the inputs. So whatever is the past value of X or the past value of Y, that does not have any impact on the output. The output only depends on what is the present value of X and Y. And that is something that we've been trying to capture in the form of a truth table. For example, the output F here in the form of a truth table, F only depends on what the present value of X, Y, Z is. And it doesn't really matter what the history of the input X or history of input Y and history of input Z is. Right? So those circuits where the output depends only on the present values of inputs, those circuits are called combinational circuits. And those are the circuits that we have looked at so far in this particular course here. And well, such circuits are limited. Combinational circuits are limited in terms of what you can do. Well, you can look upon a combinational circuit as a decision-making machine. Decision-making in the sense, for example, let's say we say that we will do something only when, let's say, the function f takes on value equal to 1. And so we will do only when f takes a value 1. And when does f take a value 1? When x is equal to 0, y equal to 0, and z equal to 1. Or when x equal to 0, y and z both are equal to 1. Or when x is 1 and both y and z are 1. So we are, the truth table and its implementation is like a decision-making system. And we realize that a decision-making system, you can look upon, as we are saying, a combinational circuit as a decision-making system. And a decision-making system which takes a decision only on the present values of input is a very limited decision-making system. We all realize that if we're talking about slightly intelligent machine, it should depend on not only what is happening now, but also what happened in the past. So memory is an essential component of something being called an intelligent decision-making system here. So that is what we do in sequential circuits. So in sequential circuits, a general block diagram is, so it has a combinational circuit block Z, but Z depends not only on the present values of X, but note that X is also fed into the storage elements, and storage elements they store the past values of X. So the present value of Z not only depends on present value of X, but also depends on the past values of X. And we've also fed back Z back into storage element and into the combinational circuit here. So Z depends not only on present values of X, but past values of X, because once it goes into a storage element, it goes into a memory. So past values of X and also past values of Z here. But note that Z is in any way a function of X. So what we are saying is that the present value of output depends not only on the present values of input, but it's a function of something that happened in the past also. So that's a more general decision-making machine, a more intelligent decision-making machine, which we classify as sequential circuits. But let's continue first. In the next lecture, we'll look at sequential circuits, the basic building blocks of sequential circuits in more detail. In the present lecture, let's continue with our discussion related to combinational circuits, because you realize that the combinational circuit, CC combinational circuit, is also an essential part of sequential circuit. Sequential circuits are nothing but combinational circuits with storage elements, along with storage elements and some manner of interconnection and all that here. All right. So once you know how to design a combinational circuit and you know how to implement storage elements, then we would be in a position to implement sequential circuits also. All right, so we've seen this, that combinational circuit starts with a description of the system in terms of the output variables and the input variables here, and capturing that in the form of a truth table then transforming a truth table into a Boolean expression here, in this case sum of product expression here. And then we minimize the Boolean expression. Minimization means we try to simplify it, reduce the number of terms, and also make each term as simple as possible. So we get a simplified expression here. And we then map it onto a network of gates. So we've already seen how to do the minimization part. We looked at a method called the method of Carnot map, K-map, a method of representing the truth table in the form of a matrix, which helps us to apply the principle of minimization easily and to get a minimized expression. Let's briefly look at this mapping of minimized Boolean expression onto the network of gates. So realize that in this, when we are talking about digital circuit design, our interest is not just in designing a circuit which will implement, let's say, the truth table or the functionality of the system, but also we want to design a system which is efficient, which takes up the least amount of area, which has the best performance in terms of that it has the least delay when I go from input to output. And it has those features. It consumes the least amount of power. And so in terms of, so what we would like to do is, for all these reasons, the least area of the circuit implies least cost of the circuit here. So for all those reasons, we would like to implement the minimized expression, Boolean expression that you see here, using the most simplest or the simplest possible circuit that we can. And so let's look at this. We'll not go into too much detail, but let's look at this mapping of a Boolean expression, minimized Boolean expression onto the network of gates here. Okay, so what happens is, let's say you have a Boolean expression like this, and there is a straightforward implementation. Of course, each one of these product terms is like an AND gate here. And wherever you require a complement, you put in inverter here. So you have each term is an AND gate, and then you combine all of them together through this OR gate here. So that's a straightforward implementation. But what happens is, depending on the technology that you're using, some gates may be easier to implement as compared to the other gates. So for example, we've been talking about MOS technology, metal MOSFET-based technology. And in MOSFET-based technology, what is easier to implement, what is simpler to implement is a NAND gate or a NOR gate. In fact, NAND would be simpler than a NOR gate, and an inverter, of course. And if you want to implement an AND gate, so the way you would implement an AND gate is you would use a NAND gate and then followed by an inverter. If you would like to use a OR gate, then the way you would implement is you would first make a NOR gate, then followed by an inverter. That's because of the nature of the technology, the way we implement gates using N-type and P-type transistors. We saw that briefly earlier, how we could implement a NAND gate and an inverter using those N-type and P-type switches. And so what we are saying is that when you're trying to map a Boolean expression onto a network of gates, what you usually have is a library of gates available, different type of gates that are available. And different type of gates will have different cost associated with them. So this is a relative cost. For example, inverter is the simplest element. So let's say assign a cost of 1 unit. 2-input NAND gate has a cost of, let's say, 2 units here, which means that its complexity is twice as large as compared to inverter. If you go back to our earlier lecture, we had used 2 switches to make an inverter, and a 2-input NAND gate, we had used 4 switches. Of course, the complexity is not directly proportional to number of switches, but that's an indication that a 2-input NAND gate is more complex than an inverter. And just for the sake of illustration, let's say it has a cost of 2. A 3-input NAND gate, let's say, has a cost of 3. Now in this MOS technology, you can also implement a single gate which does this here, which does an AND operation plus an OR operation and a complement operation. So it does all 3 of them together, and it has the same complexity as a 3-input NAND gate here. So it's called an AND or invert. There's an AND here, there's an OR here, and there's an invert here. So it's called an AOI gate here, AND or invert gate. So the point is that you have in general a library of gates available. Of course, you have a AND gate also. And as I said, AND gate would be made up of inverter plus NAND, so its cost would be maybe 2 plus 1, 3 units here. And so, and you would have a OR gate also. So you have a library of gates, and different gates will have different costs, area cost associated with them. And so the task is, how do I map it onto a network of gates such that the overall cost, so overall cost of implementing that particular circuit is minimal. Overall cost meaning if I sum up the cost of each individual unit, and then that would be the overall cost of the circuit. So that's the goal of when we are mapping a Boolean expression onto a network of gates. One of the objectives would be to map it in such a way that the overall cost of the circuit in terms of these individual cost of the gates would be minimum. Sometimes there may be some other objective. The goal is not so much as to minimize the area or minimize the cost. The goal is to make a circuit which is the fastest possible circuit. And often the two goals conflict with each other. The faster circuits are often not the least area circuits, and the least area circuits are many times they have more delay associated with them. Anyway, so that's a complicated topic on how to take a Boolean expression and map it onto a network of gates such that the overall cost is optimum or minimized. But let's look at, for example, let's say in a library there's only NAND gates available, and we would like to map our circuit onto only NAND gates. So we've already said that NAND gate is a universal gate, meaning that you can implement an inverter using a NAND gate, you can implement a OR gate, and you can implement a AND gate. These are the three basic operations in Boolean algebra: inversion operation, AND operation, and OR operation. If you can do all three using a particular kind of a gate, well, then you can do entire Boolean algebra, all Boolean expressions using that particular gate here. So if you have a NAND gate, 2-input NAND gate, you can short both the inputs together, and of course it acts like an inverter. So NAND operation is the two inputs x dot x bar here, so x dot is x here, bar here, so it's an inverter. A NAND gate followed by an inverter, that becomes a AND gate here. So that's straightforward. So we can implement an AND gate also here. This is x dot y bar, and this becomes xy here. A NAND gate, and if you feed in the complement of the input here, so if you feed in x here, so it becomes x bar, this becomes y bar here, and this becomes x bar dot y bar whole bar here. Apply De Morgan's theorem here, so the AND operation becomes OR, and the complement of a complement, then it goes away, so you get x plus y here. So that's an OR operation. So an SOP expression, a sum of product expression, is easily implemented with NAND gates. So for example, f equal to AB plus CD plus GH. So what we can do is, first, each product term is implemented like a AND gate that you see here, and all the product terms are combined using an OR gate here. So now if you would like to implement this expression only using NAND gates, so what you do is you take this AND gate and implement it using a NAND and an inverter like this here, right? So we implement it like this inverter here, and the OR gate is implemented as a NAND with inverters in the beginning here. So you implement it here, right? So this represents the AND network, and this represents the OR network here, the OR part here. And so we know that when two inverters are in series, so we can combine them and in fact eliminate both of them here, right? So this AND and OR kind of a network can be replaced by, if you eliminate these inverters, by this one here. So there's a direct mapping of AND OR network to a NAND network here. All you need to do is all the AND gates are replaced by NAND gates here, and the OR gate is replaced by a NAND gate here. And so the entire implementation is done through NAND gates here. So there's a one-to-one mapping between AND OR network and a NAND network. And why is AND OR network important? Because our sum of product expression can be mapped into AND OR network here. And then, well, AND OR network can be mapped into a NAND network like this here. So the entire circuit can be implemented using NAND gates. Well, you know, so there's a lot of optimization that can be done when you're implementing. So for example, consider an XOR gate, F equal to A bar B plus AB bar here. Well, you could implement it using this form here. A, you get A bar here, B here, so you combine them, so you generate A bar B term here, and then you generate AB bar term here, and then you combine them like this here, right? So that's a straightforward implementation of the circuit here. And then of course you can convert it into a NAND network here. So this part is converted into so you can take this here and map it onto a NAND network here. So the inverters are implemented here, and will become a NAND followed by, so this is an AND OR network here, and we've also already seen AND OR network is basically NAND network here, right? So we can implement it like this. But note that we can take this expression, note that this is already minimized expression. You can't do any further minimization, but there is a lot of manipulation that can still be done with this expression, which allows a more efficient implementation. So for example, A bar B, we can add a BB bar here, because BB bar is nothing but 0, and we can add a AA bar, which is also 0, but then it allows us to factor. We can take B out and we get A bar plus B bar. We can take A out and A bar plus B bar. So note that if we implement A bar plus B bar and then use it to generate this particular term here, and then use it to generate this particular term, and then that becomes more efficient here. So what we do is we take AB and we feed it into a NAND network here, and that gives us AB bar here, which is nothing but A bar plus B bar here. So this term in the bracket we generate here, and then we combine it with A here, we combine it with A to generate this particular term here, and then we combine it with B to generate this particular term here, and then the two terms are combined together to generate here, right? So this is an alternative implementation of the same XOR gate, but note that we have here 1, 2, 3, 4 NAND gates here, and here we have 5 NAND gates here, right? So a minimized expression and results in, and we are given that you can only use 2 input NAND gates. So a minimized Boolean expression can be implemented in 5 gates like this here, but with some rearranging of terms of the minimized expression and seeing what term can be factored out, we could implement it also like this here, and we can get a more efficient implementation, right? So beyond minimization that we have done here, there is also further sort of a minimization that can be done in terms of rearranging the terms and seeing what is common, so that the common term can be implemented only once and then reused at several places here. All right, so there's a lot of scope for optimization in these circuits that are there here. Well, implementation using only NOR gates. So note that NOR gate is also a universal gate. If you short both the inputs, you get an inverter. So that's fine. If you use a NOR gate and followed by an inverter, you get an OR gate. So we can implement an OR operation. And if you take a NOR gate and feed in the complements of the input, basically you get an AND gate here, right? So you get an AND gate. So why this interest in NOR gate? Well, NOR gates are very useful if you try to implement a Boolean expression which is in product of sum form here. So when you have product of sum, so each term is a sum term, and then overall expression is a product of those sum terms here. So that's why we call it POS here. So when you have a POS expression, product of sum expression, so each term you implement it using an OR gate, and then you combine all these terms using an AND gate here. So it's a complementary way of implementing OR AND network here. Now note that OR can be implemented using an NOR and an inverter here, and this AND here can be implemented with a NOR with inverter in the beginning, right? And these two inverters, then we can combine them together and eliminate it here. So this is my OR network, and this is my AND network here. And so we combine them together, we get this simplified circuit here. So note that there's a one-to-one mapping between OR and network and a NOR network here. So when you have a POS kind and you have an OR and an AND, Well, there's a one-to-one mapping. You can directly replace all the OR gates by NOR gate here, and you can replace the AND gate by a NOR gate here. So it becomes a completely, the full implementation is done using NOR gates here. To implement SOP expression using NOR gates. So normally we would implement SOP expression using, let's say, NAND gate, but let's say you're given only NOR gates here, and you would like to, and the expression is given as SOP, and you would like to implement using NOR gates. So the idea is that from SOP, determine the first POS expression. And then once you have a product of some expression, then it's straightforward, we just saw, to implement it using NOR gate here. So for example, there is an expression like this, it's in a sum of product form, and you want to implement using NOR gates. So what is the process? Well, we would like to get a POS expression from here. So to do that, from the Boolean expression, we would like to generate the K-map. And to generate the K-map, note that K-map has all the terms in it, X, Y, and Z here. So this is a min term. Right now, this is minimized, it doesn't have a Y here. So what we do is, the term which is missing, we add it up by putting a Y plus Y bar here. Note that Y plus Y bar is nothing but 1, so it leaves the expression unchanged here. So Y plus Y bar. Similarly, Y is missing here, so we add Y plus Y bar here. So now we expand it, and then we fill up our truth table, or we fill up our K-map here. So note that X bar, Z bar here, X bar, Z bar here. So it basically turns, we put a 1 here, and we put a 1 here, X bar, Z bar here, right? So that's, and similarly this one, XZ is filled up with here in these two. So once you expand it, you will see that these are the ones here. And the rest of the terms are all 0. Fine. So so from a minimized Boolean expression, you can generate a K-map by, if you have a minimized term, add the missing terms, okay, using this particular procedure here, and fill it up, and then develop a product of some expression, which we've already seen how to do this. We can encircle this, we can encircle this one, and we get this one here. Now this one, X bar plus Z and X plus Z, we can implement using a OR AND network. So each term is an OR term, and this term is also an OR gate here, okay? And if an inversion is required, of course you put an inverter there. And then you combine all the sum terms together using an AND gate here. So now we have said that there is a one-to-one mapping onto a NOR gate here. So we take this, convert it into NOR, we take this NOR, and we convert this into NOR. Right, so this becomes a complete NOR implementation, NOR gate implementation of this particular expression that you see here. Similarly, the product of sum expression, if you have a Boolean expression in the form of product of sum, and you want to implement it using a NAND network, so then what you do is take a product of sum expression from there, go to a K-map, and from the K-map get a sum of product expression, and then we know how to implement sum of product expression using a NAND network. All right, so let's look at then if we have circuits which are more complex. So far we've been talking about circuits whose description we've been trying to capture in the form of a truth table, then we are getting a minimized Boolean expression, and then implementing using a network of gates. But this approach will become difficult. So this particular example will illustrate that. So let's say we are talking about a 8-bit adder. 8-bit adder meaning each input A is 8 bits here, and B is also 8 bits. And then, and so 0 to 7 denotes 0 to, this is 0 to 7 meaning 8 bits here, this is 0 to 7, 8 bits here. So the sum is 0 to 7, 8 bits here, and there would be a carry also. So the output is the sum, 8-bit sum, and 1-bit carry. And the inputs are 2 8 bits. So we know what an 8-bit adder is supposed to do. So we can capture the description in the form of a table, truth table. So the truth table on the left-hand side has all the inputs, and on the right-hand side it has all the outputs. So we have 8 lines here and 1 line here. So we have 9 output lines here, and we have 8 lines here and 8 lines here. So we have 16 input lines here. And if we try to write down the truth table, so note that truth table means A is from 0 to A7 and B is from 0 to B7. It means A0 can take value 0 and 1, A6 can take value 0 and 1, and similarly every bit can take value 0 and 1 here. And therefore the different possibilities, the different possibilities for the inputs are 2 to the power 16. Because this can take, if you each bit can take 0 and 1, and there are overall 16 bits. So there are 2 to the power 16 possibilities that are there here. And corresponding to those 2 to the power 16 possibilities, there would be some expected value of S7 and S6 and so on and so forth. So we see that truth table becomes unmanageable. 2 to the power 6, a truth table with 2 to the power 16 entries is totally unmanageable. And therefore what we are saying is that this way of designing circuits, where we said that given the system description, capture it in the form of a truth table, get a Boolean expression, minimize it, and then map it onto a network of gates. Well, this, although perfectly general, but when the circuit becomes complex, this kind of an approach will not work here. We'll not be able to capture it in the form of a truth table at all. Forget about getting a minimized Boolean expression here. And so we need a different way of implementing complex combination circuits. Complex in the sense that they have not just 1 or 2 or 3 inputs, but they have, most of the time when we are processing the data is 8-bit data, or it could be a 16-bit. We are all working on machines which are 64-bit machines. And in the 64-bit machines, the addition and subtraction and multiplication is occurring on 64 bits. And you can imagine if you have a 64-bit adder, this is only an 8-bit adder. You can imagine a 64-bit adder where each input is 64 bits here. 64 bits here, 64 bits here. Output may be 64 bits here and another bit here. So trying to capture everything in the form of a truth table is just out of question. And we also realize that it's not necessary also. And so in many of these cases, what we do is we use a different approach. We design a system as a network of subsystems that are of manageable size and can be implemented using the earlier approach of truth table. So the idea is that this 8-bit adder that you see here, what we can think of is implementing an 8-bit adder as a network of, we said network of subsystems. So our subsystem is a part of a system. So our subsystem is a 1-bit adder. So we think of 8-bit adder as a network of 1-bit adders like this here. So basically, we know how to carry out 8-bit addition. So here we are just trying to illustrate a 4-bit addition here, 2 4-bit numbers here. We know that our algorithm for doing 4-bit addition is we take individual bits and we add them up, and then we use a if there is a carry, then we pass it on, and then we do bitwise addition here. So what we can see here is that this 8-bit adder can be implemented by using 1-bit adder here. So when you're doing 1 plus 0 here, you use a 1-bit adder here, and if there's a carry, then you have to do a full adder here. So that's what we call a full adder, is something that can add 3 bits at a time. So you can feed it into this. So we'll see that later on. So the point is that we don't directly take our system description and convert it into a truth table. We try to implement the system in terms of some simpler block here, a simpler subsystem here, which is 1-bit adder. This 1-bit adder now is a simple enough block that we can use a truth table approach, truth table, Boolean expression and all that, and implement it in that particular form here. Okay. So what we are talking about is a general approach that when you have a system, you break it up into a network of subsystems. And depending on the complexity, each one of these subsystems that you have, you may further break it up into more blocks here. And after that, those blocks may be simple enough to implement using our truth table approach that you see here. Okay. And so what happens is that when you're trying to take a system and implement it into subsystems, a series of subsystems, and the subsystems itself are made up of further blocks. There are several blocks which we find that are employed at many different places here. For example, there are blocks which we call as a decoder block or an encoder block. We find that in many places when we are trying to design a combinational circuit, a decoder block is very helpful here. And therefore what we can do is decoder could be one of the subsystems that are there. Adder, subtractors blocks are very common. Multiplier blocks are common. Comparators are there. And like that, there are several blocks that are there, which are very useful. And you can think of implementing the system in terms of those blocks that are there. And so those blocks, the designs are standard designs. And so you don't really have to design them from scratch. Those blocks are available and you can use them. And after using all those major blocks that are there, if you're still left with a piece of circuit which does not fall into those standard blocks, then you could then design it using your truth table Boolean expression kind of an approach that is there here. So let's look at these. These are useful blocks. So let's look at a few of them in this particular lecture here. So let's look at the decoder. So decoder, as its name indicates, its purpose is to decode, and which means to map a smaller number of inputs to a larger set of outputs. So that's a decoder in general. So decoding means the information is present in a compact form, and then you expand the information so that it's more readily understandable here. So we have what we call as a 2 input to 4 output decoder here, also called 2 to 4 line decoder here. And so 2 to 4 line decoder, what it does is, you can see it in the truth table here. And so the idea is that, when you have a 2 input here, these 2 inputs they can range from 0, 0, 0 here to 1 to 2 and 3. And so we have 4 output lines here. So if it is 0, 0, then the output Y0 is 1 and all other outputs are 0. On the other hand, if it is 0, 1, then Y1 is 1. And if it is 1, 0, meaning 2, if the input is 2, then the line 2 is 1. And if the input is 3, then the line 3 is 1. All others are zeros at that time. So by looking at these lines here, we can immediately tell what the input is, right? So for example, we would like to know when one could have a data which is continuously coming, and you would like to know when is the input equal to 2. Well, then all you need to do is monitor Y2 line here. Whenever a 1 occurs on that particular line here, you know a 2 has been received on the inputs that is there here. So this is what we call as a decoder here, right? With this kind of a truth table here. So only one of the lines is 1, and that corresponds to the value of that particular binary number here. So this is 2:4 decoder here. Now there are decoders which is similar to this, but you see these bubbles that are there here. And in this case is the opposite. If you have a 0 here, then only this line would be 0, all others will be 1 here. So this we call as active low. So most of the time, here for example, we are calling this circuit as when an output line is active when it is 1 here, right? So otherwise this particular line is all the time 0 here. But when a 0 is received here, this particular line becomes active and we put out a 1 here. Similarly, when a 3 is received here, then this particular line is active and we put out a 1 here. So in this case, the active line is denoted by a 0, and that's why we call it an active low. So for example, when a 3 is received on this line, then that particular line Y3 becomes 0 here. And all other lines are 1, 1, 1 here. So the active line is denoted by 0 rather than 1. And this bubble indicates that. The bubble here is sort of an inversion operation. So it says that the circuit is active low here. So when that line will be active, its value will be 0 rather than 1. While this is an active 1 circuit here. All right, so decoder circuits. So if you're wondering where can I use it? So for example, let's say there are these machines 1, 2, 3, 4, and as a user, you would like to control these particular machines. Let's say enable this or disable these machines here. And so if you're located in some remote location, and then you would need a line here running from close to you to the machine here, right? And in this particular format here. So imagine that you are located some 100 kilometers away, and these machines are located far away from you, 100 kilometers away. And then you will need 4 lines here, 4 long distance lines that run from your location to those machines, M1, M2, M3, M4. And note that laying those 4 lines is a costly affair. Long distance lines is a costly affair here. And so, but we don't need to do that, right? What we could do is we could run 2 lines. We could run 2 lines, long distance lines. And close to these machines, we can have a decoder, 2 to 4 decoder here. So you can control all these 4 machines using basically 2 lines here. So if you put 0, 0, well, the decoder will put out a 1 here and will enable machine 1. If you put 1, 1 here, then the decoder will put a 1 here and will enable this machine 4 here. So note that instead of running 4 long distance lines here, you can only, you can minimize by running 2 long distance lines. And then close to the machines, put a decoder here, right? So it minimizes the number of lines that need to run from one place to the other place here. You need to run only 2. So here the saving is from 4 to 2. But imagine that if you had 16, so if you had 16 machines here, you would have had to run using this approach 16 lines. But now if you have a 4:16 decoder, then you have to run only 4 lines, right? So the saving can be considerable here. So that's just, there are many advantages of decoders, many places where decoder is used. This is just to illustrate that one place where this can be useful here. Now, many times the decoder block that we just talked about has a enable input also. So the idea, and this enable input you will see in many digital blocks. So the idea is that there's a block of circuit which performs some function, but there's an enable pin here. So when you see enable here, this is an active high enable. So when you put a 1 here or a high here, then the block is enabled. It means it will work like according to its function. But if you put a 0 here, then it doesn't really matter what you put A, B here, the whole block is disabled. So in our case, what it means is the following. If we put E equal to 0, enable equal to 0, which means we are disabling this block, then it doesn't really matter what is A and B. X denotes as don't care. It could be 0, 1, anything it can be. B can be 0, 1. The outputs are, all the outputs are 0. So it doesn't really matter what the inputs are. The whole block has been disabled. All the outputs are 0 here. On the other hand, the moment you put enable equal to 1, now the circuit starts working as expected. So when you have 0, 0, then Y0 is 1. When you have 0, 1, then only Y1 is 1. And when you have 1, 1, only Y3 is 1. So many of these circuit blocks and digital ICs, they have an enable pin here. And it's a very useful feature. At any time, you can enable a block or you can disable a block using a single input, that is here. And the enable input could be active low also, meaning that if you give a 0 here, then that will enable the block. On the other hand, if you give a 1 here, that would disable the block. So when you see a bubble, it means it is active low. So on the low, the circuit will start functioning here. So if you put a 1 here, well, the circuit is disabled. On the other hand, if you put a 0 here, then the circuit works like a normal decoder block. So this is a very useful feature that is there here. And so how do we implement a decoder using gates? So because it's a useful block, let's see how we can implement this here. So that's the truth table here, the truth table of a decoder. So once enable is 1, then 0, 0, we've already seen Y0 is 1, 0, 1, and so on and so forth. So the implementation is very straightforward. If we look at Y0, note that Y0 is 1 only once. So there's only one term in it. And the one term is what? Enable has to be 1 E, and then B is 0 and A is 0. So B bar, A bar, that's it. Y1 is 1 only for one term here. So that will be E, and then B bar, and then A. So like that, we can write it up, Y0, Y1, Y2, Y3. And therefore, we can implement it in the form of a gates here. So each term is an AND gate here. So Y0 is generated through an AND gate with the input E and B bar, A bar here. So A fed through an inverter is A bar, and B fed through an inverter is B bar here. So you can see that it will be equal to E B bar A. And similarly, all the terms that you see here. So very straightforward implementation. All you need to do is generate all possible terms here. B bar, A bar, B bar A, B A bar, B A. All possible terms that are there in the two input variable. You generate them, combine them with an enable signal, and you get all the Y0, Y1, Y2, Y3. So very simple, straightforward implementation here. Note that when we are doing a decoder, we are generating all the terms that are there here. B bar A, B bar A, B A bar, B A. In a two input variable, these are all the terms that are there here. There are no other terms. So a decoder circuit generates all the possible min terms that are there here. So that's, we can take advantage of. Okay. So that's what we are saying. 0, 0. This is 0, 0 term here. This is 0, 1 here. This is 1, 0 here. This is 1, 1 here. So it can be used to implement any combinational circuit. So note that a combinational circuit is what? That for some combinations of inputs here, for some of the entries in this truth table, the output will be 1. Well, we could do that. For example, let's say there's a function here, and it is 1 when it is 0, 1, and when it is 1, 0 here. And for others, it is 0 here. So suppose we have instead of designing a circuit from scratch, suppose we have a decoder block like this here. So first thing is we enable the decoder block. And then note that for 0, 0, it is 0. So we leave it as it is. Y0 is related to the 0, 0 term here. Note that B bar, A bar here. Y1 is related to B bar A here. Okay, so this term Y1 is there. This 1, 0 is Y2 is there. So if we take these two terms and we combine them using an OR gate, we get a function f. How? Well, anytime when we have 0 and 1, when we have 0 and 1 is basically equal to Y1. So this term will go 1, and therefore our function fed into an OR gate will go 1. Anytime we have 1, 0, well, then Y2 will go 1, and through an OR gate, it will make f equal to 1 here. So if we have a decoder with us, so decoder, what it is doing is generating all these terms here. 0, 0, it is this term here. 0, 1 corresponds to Y1, 1, 0 corresponds to Y2, and 1, 1 corresponds to Y3. Meaning that when B and A are 0, 0, then this will become 1. When B and A are 0, 1, then this will become 1 here. So all the terms that you see are generated. And a function only uses a few of those terms. So whichever terms are required, we take those terms and we combine them through an OR gate and we get a function here. So given a decoder, you can implement any combinational, any truth table in a very simple form. So the idea is that if somebody designs a decoder, and let's say 2:4 decoder, right? 2-line to 4-line decoder. Well, any function of two input variables you could implement using this decoder here. You don't have to design the circuit. All you need to do is use a decoder and use an OR gate, and you have a combinational circuit which is ready. Okay, so that is there here. So for example, if you have a 3-input truth table here, well, you could implement using a 3 to 8 decoder here. So just for the sake of discussion, we have shown a circuit which is active low. So it is active low, and not only that, the output is also active low. Meaning that, for example, so to enable this, you will have to put a 0 here. And if you have 0, 0, 0 here, then it means Y0 is active. Y0 is active means this particular line will go to 0. All other lines are inactive, which means they will all be 1 here, because the circuit is an active low circuit here. Okay. And so what we do is basically then we look for those terms for which the function is 1. So it is 0, 0, 0 here, so it corresponds to Y0. Then we have term number 2, so we take second term here. Then we have term number 4, so we take this 4 here. And we combine them together using a NAND gate, and we feed in here, right? So how? Well, say when you have 0, 0, 0, right? 0, 0, 0 here. Then what will happen is this term will be 0 and all other terms will be 1. And if you feed in a 0 to a NAND gate, you'll get F equal to 1 here. So for a NAND gate, the moment one of the input is 0, the output is 1. Okay, so that turns out to be true here. All right, so similarly you can check out here. So when 0, 1, 0 is there, then all other inputs will be high except for the input number 2 here. So that will become 0, and that will also turn it to 1. Right, so the idea is that any combinational circuit of 3 inputs can be implemented with a decoder, 3:8 decoder. And the decoder could be active high, like the previous case that we said, and the decoder could be active low also. When it is active low, we use a NAND gate to combine all of them. When it was active high, we used a OR gate to combine all of them. Okay, so now, for example, it can happen that you require a 3:8 decoder, but then what you have available is only 2 to 4 decoder. Or let's say you have you require 4:16 decoder, and what you have available is only 2 to 4 decoder. But that's not a problem. We can combine simpler decoders to generate larger decoders here. All right, so let's see here. So you want a 3:8 decoder, and you have only 2 to 4 decoder here, 2 input to 4 here. So you can use 2 of them. Both of them have an enable pin here, so you can use 2 of them here. So A and B that you see here, we feed into A and B here and A and B here. And the input C that you see here, so we use an enable, and C we feed in here, right? And one of them is always 0 here. And this one we feed it to enable input of the first decoder, and the second one feed into the input of the second decoder here. And with this approach, you note that now you have 3 inputs, A, B, and C here. And with these 3 inputs, we can get the complete 3:8 decoder here. Y0 to Y3 is available on the first decoder here, and Y4 to Y7 is available on the second decoder here. Well, how? Well, so note that when C is 0, right? So let's look at it here. So let's see the whole thing here. So when C is 0, so let's put enable equal to 1, and let's put C equal to 0 here. So when C equal to 0, then what will happen is we have 0, 0. This line is enabled, right? This is 1, and this decoder is enabled. All other lines are 0, right? So this decoder is disabled. Disabled meaning all these values will become 0, 0, 0 here. Okay, so these are all 0, 0 here. And what you're doing is basically realizing this part here, right? So when E is 1, E is 1, so obviously, so there, C is 0. So when C is 0, so this particular one is enabled. And depending on the value of AB, either this line will go high, or this line will go high, or this line will go high, or this line will go high. All others are 0, 0 here. Okay, so Y4 to Y7 are all zeros that you see here. And depending on BA, either Y0 is 1, or this one is 1, or this one is 1, or this one is 1. And all others are 0, 0 here. So, and when C goes 1, here, so this works fine here, you can see. And when C goes 1, this particular decoder block is disabled, this one turns on. And now Y4, Y5, Y6, Y7 will generate. All others will be 0, 0, 0. And depending on the value of AB, either Y4 will be on, or Y5 will be on, or Y6 or Y7. So that particular part of the truth table will be realized by the second decoder here. So you can combine simple decoders and generate more complex decoders using this particular approach here. And you can see that the enable pin is very useful in this. If we didn't have an enable pin, then we couldn't have combined the circuit blocks in this particular manner here. There's a special decoder which we call as a 7-segment decoder. And so the idea is that when we are doing computation, and we would like to display the results of the computation, and one very simple way of displaying that is on what we call as a 7-segment display. So the display is made up of these segments, decimal digits that are there here. And so this is 1 digit that is there here. And each one of these A, B, C, D, E, F, G that you see here is an LED here. So it's an LED here. And by lighting up these LEDs in a selective manner, you can display any digit that is there here. You can display from 0, you can display 1, 2, 3, up to 9 here. So that's why we call it this is a single digit display here. And so for example, you could see if we light up all of these and we don't light up anything in the middle, then that's a 0 here. On the other hand, if we light up A, F, G here, you can see this is a 5 here. And if we light up here, you can see this is a 9 here. So depending on which LED we light up, we can get a different number here, 0, 5, 9, 2, 3. So any of the digits we can display on this particular, this is called a 7-segment display here. There are 7 segments here, and that's called a 7-segment display here. So each one of these LEDs is, note that each diode is nothing but an LED here. So all these LEDs, they have their cathode shorted together through a resistor here. The purpose of the resistor is to control the current. And note that if I apply high voltage here, let's say 5 volt to all of these here and 0 here. So what happens is 5 volt here will turn the LED on, current would flow, so this will turn on. So the segment A will turn on, A, B, C, D, E, F, all the segments will turn on except for G. So basically we would display a 0. We would display a 0 on our display there. And depending on what we feed in here, A, B, C, D, E, F, G, so what values we feed in here, we will get different displays that are there here. And what values we feed in here is nothing but a binary value here. So in this case, the binary value is 1, 1, because high is equal to 1. So we have fed in 1, 1, 1, 1, 1, 1, and 0. Now you may think that if you feed in, let's say, you can think of how would you get a 5 here. So to get a 5 here, A will be equal to 1, then B will be equal to 0, C will be equal to 1, D will be equal to 1, E will be equal to 0, F will be equal to 1, and G will be equal to 1 here. So if we feed in that binary data here, then we will be able to display 5 here, and accordingly. So different binary number here. So it's a 7-bit binary number here. There are 7 segments, 7-bit binary number here. We will get a different digit here. So the idea is the following. We have a normal binary number here, which ranges from 0000, which corresponds to 0, to maybe 1001, which corresponds to 9. So we have this binary number representation of a decimal digit, and we would like a decoder. Decoder maps lesser number of input to larger number of input. So we would like it to, for a particular number, binary number here, or a decimal digit here, we would like it to generate and appropriate these values here, so that when I feed it into my circuit here, then the appropriate number will light up, a number which corresponds to the decimal value of these numbers here. Okay, so basically then we have this kind of a truth table here. So for example, if A, B, C, D, the number is A, B, C, D here, then note that I want all A1, B1, C1, and all that, only G equal to 0 here, and like that we can get a truth table here. Okay, so we can generate all these different numbers that are there here. And this is what is called a 7-segment decoder. So we'll not go into the details here. For each one of those outputs A, we can write a truth table in terms of D, C, B, A, and figure out what the circuit is. And so let me just illustrate. The final circuit would be something of this kind here. So you feed in the inputs A, B, C, D here. There is a blanking input, but let's not get into that. And you can get all the values here, A, B, C, D, E, F, G here. So that's a decoder also. It's called a 7-segment decoder. And because 7 segments are very popular for showing the results of the computation on the display, the 7-segment decoder ICs are commonly available. And you can feed in your 4-bit data, and it would display on the 7-segment display the decimal digit corresponding to that particular binary data here. All right, the opposite of a decoder is an encoder. So what it does is it takes more number of inputs and maps it onto a lesser number of outputs that are there here. So for example, a 4:2 encoder. So it takes four lines and maps it onto 2 lines here. So when you have 0001, it makes it 00 here. Similarly, 0010 here makes it 01. 0100 here, 10, and 10 equal to 11 here. So one of these lines is active at one particular time here. Either this particular line is active, this data line is active, or this one is active, or this one is active. And then this is mapped onto a 2-bit number here. So encoder, and there are various kinds of encoders that are there here. And an encoder like this here, we can write down what is A or what is B in terms of D3, D2, D1, D0 that you see here. Okay, and then we can map it onto. Note that the rest of it doesn't really matter what it is. So it's like a don't care state here, a don't care state here. So we can write down an expression for A, we can write down an expression for B here. The empty boxes we don't really care. So what is important is that when this is 0, when this is 1, and all others are 0, 0, 0, then something should happen here. A should go to the appropriate value here. For other combinations beyond these 4, we have a don't care state here, so which we can utilize to simplify. All right, so that's an encoder block here. So another useful, very useful block is what we call as a multiplexer. And so this is what is the symbol that we use for a multiplexer. And this is called a 2:1 multiplexer. So the idea is that there are these 2 data lines here, I0 and I1. And depending on the value of S, we can connect the output either to this particular input, or we can connect Y to I1 here. So these 2 lines can be multiplexed onto one particular output line here. And so the truth table for it is the following. When S is 0, Y equal to I0. And I0 could be 0 or 1. If it is a 1-bit input, it could be 0 or 1. And when S is equal to 1, then Y equal to I1 here. So this I1 gets connected to this particular one here. So that's a multiplexer. We can, using the select line here, we can select either the input I0 or we could select I1. Selecting means connecting it to the output here. And so the implementation is straightforward. So this is the select here. So when we put select equal to 0, so when it is 0, if I put an inverter here, so this line becomes 1 here. This becomes 1. And when we put a 1 here, this AND gate is enabled, which means the I0 passes through here, appears over here. And when S is 0, so this AND gate is disabled, so there's a 0 here. And we have I0 here, and I0 will then pass through a OR gate here because we have put a 0 here. So the gate is open, and we get an I0 here. Note that when you put a 0 here, then if there is a 0 here, I0 is 0, so output is 0. When I0 is 1, then the output is 1. So that's why we are saying I0 passes here. Right? So when S is equal to 0, the output Y is connected to I0 here. And similarly, you can see that when S is equal to 1, then this particular gate is enabled, and you will get a I1 here, and this one will be 0. So the output Y, this will be equal to, output will be equal to I1 here. Right? So this is the very simple implementation of a multiplexer here. This is a 4:1 multiplexer. It takes 4 input lines and multiplexes it onto a 1 single output line here. And to do a 4:1, you require 2 select signals here. So when you have 0, 0, I0 is connected to Y. When you have 0, 1, I1 is connected. So 0, 1 is indicated here. When you have 1, 0, meaning S1 is 1, S0 is 0, then I2 is connected to Y, and like that I3 is connected to Y when input signal, when the select signals are 1, 1 here. And the implementation is straightforward. Each one of these, so you require for each combination of, for 0, 0, you use a gate like this here. So when you use a gate like this, you feed in I0 here, and when it is 0, 0, then these lines become 1, 1, and the gate is enabled, and I0 comes here. I0 comes here and then it goes here. All other lines will be 0 here. Right, so a straightforward implementation of a 4:1 multiplexer here. Now mux is used when, for example, is very useful when resources have to be shared. So for example, let's say we have an 8-bit adder, and 8-bit adder is a fairly complicated circuit, and we would like to note that we would like to use it in as efficient a manner as possible. So note that we can use multiplexers to add up, to use this particular 8-bit adder to add up different numbers that are there here. So for example, if I have a multiplexer like this here and another multiplexer like this here, so what it indicates is when S1 is 0, so these values is 0, then this 8-bit number is able to pass in here. So it's a 2:1 multiplexer in the sense that there are 2 input lines and 1 output line, but each input is a 8-bit number here. Okay, so when you select a 0, then A goes here, right? So A goes here, and when this select is, then C goes here because it is 0 here, so C goes here, and output will be A plus C. On the other hand, you can easily see that if you want to do B plus C here, then you put S1 equal to 1 here, and then you can add up B plus C here. So with the same 8-bit adder, you could do A plus C, or you could do A plus D, you could do B plus C, or you could do B plus D here. So it's allowing us to do all these different kinds of addition using a single adder here. So the same adder is being used with different inputs that are there here. Okay. Well, we saw that using decoders, one could implement any Boolean expression. With multiplexer also, we can implement Boolean expressions here. And so if you have to design a combinational circuit, and if you're given a multiplexer, if multiplexers are readily available, then it's very easy to implement a Boolean expression. So for example, this is a 2-input Boolean expression, and we can do it, implement it using 2:1 multiplexer. So one of the variable you feed into the select signal here. And now, so this x1 is there. And so now the question is, what do I put in here, right? So let's look at it here. So when x1 is 0, so when x1 is 0, then, and if x2 is 0, then we expect y equal to 0 here, right? So let's put when x1 is 0, so when x1 is 0, it is this here. And if x2 is also 0, then y is 0 here. On the other hand, when x1 is 0 and x2 is 1, y is 1 here. So what is y in terms of x2? Y is basically equal to x2, right? So when x1 is 0, here, y is, if x2 is 0, y is 0. If x2 is 1, y is 1, which means y is equal to x2. So what we do is we feed in x2 here. So when x1 is 0, y will get connected to x2 here. Now we say, let's see what happens when x1 is 1 here. So we put a 1 here. So x1 is fixed now 1. And then we look at what happens when we change x2. So if x2 is 0, y is 1. Where do we get y equal to 1? From this expression here. And when x2 is 1 again, if we put 1 here, we get 0 here. So in this case, we see that if x2 is 0, y is 1. If x2 is 1, y is 0. So y is equal to x2 bar. So we feed in x2 bar here. So that becomes a implementation of a Boolean expression using a 2:1 multiplexer here. We feed in one of the signals x1 here, and then x2 and x2 bar we determine in this particular way here. All right, so let's look at a 3-variable function here, x, y, z, and we'll implement it using a 4:1 mux here. So one of the, so we have 2 select inputs, 4:1. So 2 of the inputs, let's say y and z, the least significant bits, we feed it here, y, z here. So what does it mean? Y, z is 0, 0. It is this line gets connected here, 0, 1, then this line gets connected here, and so on and so forth. And now we have to determine what do we put here, right, at this particular place so that this function is implemented. So let's do that. Let's put yz equal to 0, 0. Yz is 0, 0. Okay, so we want to know what should we put at this line. Then we'll focus our attention on when yz is 0, 1. What should we put on this line? So right now yz is 0, 0. So x can take two possible values. X is 0. Well, if x is 0, 0, 0, 0, we don't see it here, so f is 0 here. When x is 1, well, 1, 0, 0, so that's equal to 4. We don't see it there. It's also 0. So what does it mean? Well, for 0, 0, what should I put here? Well, it doesn't depend on the value of x. X could be 0 or 1. Function is 0 here. So f is equal to 0. So we put in 0 here. Next, we focus our attention on when yz is 0, 1. Okay, so yz is 0, 1. So let's put x equal to 0. So 0, 0, 1, 1. So 1 is there in our function, so we put a 1 here. Let's put a 1 x equal to 1 here. 1, 0, 1, 5. 5 is not there, so we put a 0 here. So what is f now? So f, how does it depend on x? Well, f is x bar here. So we put x bar here. And now we try to figure out what should we put here. 1, 0. So accordingly, we fill in here. If x is 0, so this is 2. 2 is present here, so we put 1. 1, 1, 0. So this is 6. 6 is also present, so we put a 1. So f is always 1. F is always 1. Doesn't depend on the value of x. X could be 0, f is 1. X could be 1, is 1. So we put in a 1 here. We put in a 1 here. Next we do 1, 1. Then again we put a 0 here. So this is 3, 0 here. We put a 1 here, and it is 1 here. Okay, so then f equal to x here. So we put in x here. Right, so thereby we have implemented the Boolean function, 3-variable Boolean function using a 4:1 multiplexer here. Okay. And MUX is more efficient way of implementing combinational circuits as compared to decoders because the MUX is simpler. If we were trying to implement a 3-variable implementation using a decoder, we would have used a decoder, we would have used a 3:8 decoder, and that 3:8 decoder is far more complex or significantly more complex as compared to a 4:1 multiplexer here. Now, just like we could combine decoders and generate larger decoders, similarly we can combine MUX and generate bigger MUXes that are there here. And again, in this context, the enable pin will be helpful here. So we add an enable pin here. And basically the same thing it means when enable is 0, the whole MUX is disabled, the output is always equal to 0. But the moment we put enable equal to 1, now the circuit starts functioning depending on the value of S. Either Y gets connected to I0 or Y gets connected to I1. Right, so this is an example of a 2-input 2:1 MUX. And we can combine 2:1 MUX to generate a larger value of MUX. So a larger value of MUX, which is a 4:2 MUX here. 4:1 MUX. So it has two control lines, S0 and S1. And so you can see, check here, when S1 is 0. So when S1 is 0, this particular MUX is disabled, and this particular MUX is enabled here. Enable is 1. And then depending on the value of S0, either I0 goes to Y or I1 goes to Y here. On the other hand, if S1 is 1, here, then depending on the value of 0 here, either I2 goes or I3 goes here. So if you write down the truth table for a 4:1 MUX with two select signals S0 and S1, you can see that you can use a simpler MUX, 2:1 MUX, but two of them, and combine them in this particular manner to generate that here. Okay. And so you can see here, if it is 0, then this is enabled, this is 0 here. And because this is disabled, so this input is 0, so this input to the OR gate doesn't matter. And if S0 is 1, then you select here, you get I1, and you get I1 here. So that's what happens here. When S0 is when S1 is equal to 0, when S1 is 0, and when S0 equal to 1. So when S1 is 0, S1 equal to 1, output equal to Y1 here. So you can verify that this will act like a, for all possible combinations, you can easily check that the Y will be either connected to I0, I1, I2, I3, depending on the value of S0 and S1 here. And so S0 is the normal select pin of the multiplexer, and S1 is then fed into the enable part that is there here. Okay, so you can check for other combinations also. Okay, so corresponding to a multiplexer, we have a block called a demultiplexer here. So let's say a similar kind of an example. Let's say we have these these units or these machines that are there, they need to communicate with each other. So maybe U1 needs to communicate with U11, U22, U33, U44. Similarly, U2 maybe needs to communicate with, there could be machines, could be users. So U2 wants to communicate with any of those four. And let's say these things are far apart. So now if U1 wants to communicate with any of these four, a direct communication would have required 4 lines to run here. Similarly, 4 lines would have to run from U2 to all these here, and similarly 4 here. So we would have required 16 lines to run all the way from the first set of blocks to the next set of blocks here. And so that's unnecessary. What we can do is we can use a multiplexer. So any of these users or machines could be connected to one particular line here using a mux. So we can have select signals here. So 2 select signal here. So this could be 4:1 mux here. We could select either U1, U2, U3, U4 by using the select signals here. And so this mux is close to these particular users or these particular machines. And then there is one set of line here. It could be a high speed, long distance line here. So it runs here. Now U1 may want to communicate with U11, U1 may want to communicate with U33 here. So we put a demultiplexer block here. So demultiplexer block will then, it performs the opposite function here. It can take a single input and either connect it to this particular output or this particular output or this particular output or this one here, depending on, again, the select inputs here. So the demultiplexer, what does it do? For example, this is a 1:4 demultiplexer here. So 4 output lines are there and 2 select signals are there, because when you have 4 of them, you will require 2 select signals to appropriately select this here. So basically then if S1, S0 is 0, 0, then this data line is connected to this output line Y0 here. So Y0 is X here, X meaning the data is connected to, the data X is connected here. And 0, 1, then Y1 is connected, 1, 0, Y2 is connected, and 1, 1, Y3 is connected here. So that's a demultiplexer. A single line can be connected to multiple output lines here, depending on the select signals that we have here. The multiplexer was multiple input lines are connected to single output line here. And in this case, one single input line is connected to multiple output lines here. So obviously note that this particular implementation will be far more efficient as compared to running 16 lines. You're running only one long distance, maybe high speed line here. And then you're using a mux and a demux to appropriately connect any machine, any user to any other user on the other side here. So a demux is also a very important and useful block that is there here. And implementation of a demux is very much like a decoder. If you realize that decoder was also a small number of inputs were there, and for example there was a 2:4 decoder or 3:8 decoder. Demux is also like that. There are, if you have 2 select lines, you can have 4 output lines here. If you have 3 select lines, you could have 8 outputs here. And so this is a demultiplexer, and this is what a decoder was. Decoder was, if enable is 0, then of course all the outputs are 0. But if enable is 1, then depending on 0, 0, then only this one is enabled here. This one goes high. If 0, 1, 1 goes high. If the binary number is 2, then the second line goes y2 goes high. If the binary number is 3, then y3 goes high here. So if you compare the two are very similar blocks. So if you we had already implemented decoder like this here, and so all we need to do is, if we take the enable pin here, and instead of enable we feed in the data here, and instead of AB if we feed in S0 S1. So what will happen is, now if S0 S1 is 0 0, then this particular AND gate is enabled, and if you feed in the data here, then the data will go through Y0 here. All other AND gates would be disabled. So it's the same as decoder block, and except for the enable pin here, if instead of enable, if we feed in the data here, if the data is 0, the output will be 0. If the data is 1, the output would be 1 here. On the other hand, if we put S0 and S1 is 1 1, all other AND gates are disabled except for the last one, and so the data will then appear at Y3 here. Okay, so let's stop here. We'll look at a few more blocks in the next lecture.